Okay, I have another gift for you today. By like thumbs up, thumbs down, how do we like the note sheet thing? I mean, I'm going to give you another one today. Is that okay? It allows me to go a little quicker too. I don't know. Some of you, like, I'm robbing you of the educational experience of taking the notes, like full notes. So I don't know. You can make additional. Exactly. I don't personally, as a student, derive like a lot of benefits from like taking copious notes. So I'm like a little bit, sensitive to that. Or rather, I should say, I don't personally derive no benefit from like copying down word for word things. I can do that without thinking about it. I'd rather like take intentional. Okay, so today we're moving on to section 10.2. We'll spend just one day here. Yesterday we talked about parametric functions, and the thing maybe you don't remember is that parametric functions are the same as vectors, right? Parametrics are the same as vectors, okay? That's like a big idea. And we should say a few things just to remind you about what you know about vectors then, too. Right? So that's the point of the first couple things there. And actually I could say more, right? There's tons of stuff we talked about in vectors in pre-calculus, right? You know how to find the angle between vectors and talk about like when vectors are orthogonal and all this crazy stuff. And, yeah? Remember all this? You remember the idea of a scalar is a one-dimensional quantity and a vector is a multi-dimensional quantity. We'll deal with mostly two-dimensional quantities, but all of this stuff definitely we would do in 3 dimensions for sure. Most of these concepts don't nicely extend to more dimensions than that though, but one could do it for sure, and the calculus would all work out just marvelously, yeah.
Why is temperature a scalar if you can have vectors?
So temperature is measured as a one number quantity, right? It's a real number. One real number quantifies temperature, right? So it could be negative, positive, it could be 0, right?
Oh, right.
It's a one-dimensional quantity that the point is, right? It's not like it's not like I have to deliver to you 2 numbers and communicate the temperature, right? So don't get too caught up on these if you don't like understand physics or whatever. I mean, someone will come and tell you that this is a vector or a scalar when the time comes. Yeah. Yeah, so it will become very obvious very soon if it's not already. Okay. Yeah. So don't worry. So just trust me, first of all, that these two things are intimately connected. In fact, the same idea. And let's roll with some vector review. Here we go. So do you remember we sometimes use this like bold, non-italic letter to represent a matrix or a vector. Or if in your notes, like now I printed this for you, so that's nice of me. But if you were writing it by hand, you might write like that too. Or I mean, sometimes we write it like that too, right? But somehow we want to signify that this thing is not a number. It's a vector. It's a two-dimensional and three-dimensional quantity, right? And then we have these special vectors I and j. You remember they're the unit vectors in the x and in the y directions, which means that you can write any vector like u here as a linear combination of I and j, which is a powerful idea. It sounds kind of dumb. You're like, okay, that's easy, right? But it's actually a really powerful idea. The fact that these two little baby vectors can build every vector, right? Just from these two, we can build up every vector. Remember that when you add vectors, you add component-wise, and you subtract component-wise. There's a nice visual representation, which you might remember from pre-calculus. You add them end-to-end, kind of, and get these nice parallelograms. You can multiply by a scalar. That's easy. We won't talk really about multiplying vectors. Remember, there are 2 ways you might have learned in pre-calculus to do that: the dot product and the cross product. But we don't really need those today, so don't worry about those. I'm just trying to hit the major things that we'll definitely need to know today. You remember that the magnitude of a vector is given by the Staggering theorem, and we denote it using absolute value bars, which is a really good notation because for a one-dimensional vector, remember, a one-dimensional vector is really just a scalar, right? But if you want to take the absolute value of a number, like -5, actually this definition works great too, right? It's just this, okay, well, x is -5. Okay, so I like it for this reason. And if you want to take the magnitude of a three-dimensional vector, 1, 2, 3, then that's the square root of 1 squared plus 2 squared plus 3 squared. It generalizes awesomely to other dimensions, higher and lower, right? Don't you agree this is your notion of absolute value? And I want you to, like, maybe you weren't sold on it when someone told you back in Algebra 1 or whenever you learned about absolute value for the first time. They might have told you absolute value, we want to think about that as like the magnitude. We want to think about that as like the distance from 0, right? And they were right, if someone told you that, right? You might be like, no, it's just this thing that makes things always positive. Well, that's not meaningful in the context of vectors, is it? I mean, it is true, the magnitude will always come out to be a positive number. But it doesn't make sense to just be like, oh, you just make this vector positive. What? Right, anyway, sorry, I've said too much. Go ahead.
Just out of curiosity, which concept came first? That influenced the other.
Shoes, oh man, you're asking a hard question. I don't know. Why don't you look that up for me and tell me? Yeah. I don't know. A good question. I'm curious too. I don't know. Which came first, chicken or the egg? I don't know. And then, of course, you remember how to convert from this component form to magnitude and direction, right? Find the magnitude is easy. Find the angle is a little trickier sometimes, right? But you can use some trig to get that. You won't have to find the angles associated with a three-dimensional vector in this class. So you will in multivariable calculus. So something to save for later. All right. Also, remember, if you have the angle and magnitude, you could get the component form, right? Again, using some trig. All right, so if you want more review, I put up on the first slide today, in the warm-up slide, optional reading in the book. And the book has lots of things that go into reviewing how all these terms and stuff like that. We want to get to some of the calculus. Okay, so here we go. R, we're going to use capital R, bold R here to represent the position vector today on almost, I think, every single example. People might use other letters, but that's a good one. I think sometimes people use S too, right, for position. But now I ask people who are wondering about the connection, maybe it's now becoming clearer, right? This is the position of a particle after some time t, and it's given by this vector right here. Do you see it? Oh wait, those are just the parametric equations for the position of the particle at the time t. Right. They are not similar, they are the same, right? There's no difference, in fact. It's just maybe a slightly different way to write it or something, right? But they're in fact the exact same thing. So when we're doing parametric functions, we are actually doing vector functions, right? The velocity and acceleration functions with respect to time are these, right, as you would expect. They're just the component-wise derivatives with respect to t. You could use Leibniz notation too. I think maybe your book does that. All right, so then let's take a look at this, the path of this particle. Okay, this is an interesting particle moving around in this crazy, it's called a Lissajous curve, actually, if you want to go look that up and play around making cool curves like that on your calculator. It's fun. Anyway, it's given by this equation, though. All right, you can trust me. So find the velocity and acceleration vector functions. I think you can do that right now, right, without any trouble. Just take time derivatives on both of these two components individually. This is not dy dx. This is the easy thing, right? This is just what we did yesterday. So what are we doing? Velocity. What's that going to be? 3 cosine? 3t, comma, negative 5 sine. And then take a second derivative too. Okay, got it right? Yeah, what's up?
In the sheet, the speed says dy over dt squared plus dy over dt squared.
Are we on that slide yet? You're working at it.
No, you're doing that.
No, we're not there yet.
No, we're not quite there yet. I know you're
Second stage.
It's all good.
Oh,
Right
you
now I'm
see-
asking,
oh, yeah.
so yeah, we haven't gotten to that yet. We haven't mentioned the word speed at all yet, right? Speed, as someone told you probably once before, speed and velocity are actually different, right? We want to think of speed as the magnitude of the velocity vector, right? So right now I'm just looking for the velocity vector. Boom, there it is. We will in a minute take also the magnitude of this vector. And that'll be good. Yeah. But no, good question. You're staying ahead. I like that. Okay, what about the acceleration vector?
Negative 9 sine
Yeah, what is it? Negative 9 sine 3t.
Negative 0.5 cosine part.
Beautiful, all right. So no surprises there. Moving smartly along. Yeah, but
When you're writing that down, you write just vector v or v of t.
oh yeah, you can write v of t. I mean, it's like the difference between writing y equals some function and y of x, right? Which would you prefer? Well, as long as the context is clear, I don't care. All right, so now we get to talk about speed. All right, fine. All right. So yeah, let's talk about speed and direction. The speed of a particle is the magnitude of the velocity vector. Yay, right? How do you find the magnitude of a vector? Well, you do this, right? Are you okay but with this notation?
Is that supposed to be dx?
Yeah, that's what I was.
Yeah, yeah. Maiden voyage of this PowerPoint, sorry. Okay. Good catch. Thank you for being my test audience. Okay. Thank you. So, or said another way, it's, x prime of t squared plus y prime of t using prime notation, Same thing, yeah? And then sometimes we give the unit vector in the direction of the velocity as our, to indicate just, it's a vector now pointed in the same direction but stripped of all the magnitude information, right? So to find a unit vector just in life in general, you take a vector and you divide by its magnitude. So here we're taking the velocity function and dividing by its magnitude. What you get is a new vector. This is still a vector quantity, let's be clear. Up here, this is a scalar, right? This is a vector though. It's a new vector that has the same exact direction as the old vector v of t, but has as its magnitude just 1, right? So that's sometimes people talk about that being like the direction vector or something. All right, so this is the exact same example, so let's just find the speed and direction of motion at t equals 2. We could do it also in general, but let's actually say what it is at 2. So I am not on the same flow. You guys have it written down nearby, right? We plug in 2 to to our functions. Let's see, speed, where was it? I'm going to write it down again because I can't remember off the top of my head. Velocity was 3 cosine 3t. So plug and negative 5 sine 5t. All right, so the magnitude of that would be, we're doing 3 cosine of 3 times 2 squared plus negative 5 sine 5 times 2 squared. Take the square root. Okay, so this will be our speed. Okay, give me a value there. And the direction we're giving as this this unit vector here. Let's see if we can do it. It'd be, well, let's wait maybe and find out what the speed is first, because I would like to know. Can someone give that to me with 3 decimal points of precision? I can do it too. It's not a problem.
3.962.
Can I get an amen on that? Anyone? Okay. All right, and then do you have that stored in your calculator still? Don't let it go away, right? Because we're going to need that now. The direction of motion at 2 will be this vector here, right? With that divided by 3.962, right? So I don't know a nice way to write this. Plug in 2 though into that. It'll be 3 cosine of 3 times 2 over, but like I said, use the full value please here. And negative 5 sine of 5t over 3.962. But again, use the full value there. So we'll get 2 components here. Remember, like I said, the direction is going to be this vector quantity. And then, whatever those come out to. All right, amazing. We'll wait till the end. I'm excited too. All right, so I don't know what you get there, but those would be your answers. That makes sense? So far, so good? Okay. We're going to skip for the sake of time, move on here. This is a super important idea. We'll make sure we get it. Okay, so if the velocity vector, I'm gonna name it. I hope you're okay. Are these both comfortable notes? There are like a million ways we can write these things. All right, we can also write these as dy dx dt, dy dt. Right, we have all these different ways of writing this. Okay, are you comfortable with all of them? I'm gonna use this notation right now just for fun. Okay.
Yeah.
Okay. So then the displacement of the particle is, again, not a surprise, perhaps. If you want to talk about the displacement, like how far it moved from time A to time B, then it's just the integral of the velocity functions in both directions. Yeah? Again, hopefully not a huge surprise. It's just in this new context. The distance traveled by the particle is, and this is why I had Matt do this second part of the warm-up today. I was like, let's throw back to last semester. How do you find the distance traveled? Don't you take the integral of the absolute value of the velocity function? Or, said another way, what is this then that we're actually integrating? Speed, isn't it? It's the integral of the speed. Gives you the distance traveled. That should kind of make sense. Yeah? And what is this actually in front of us? This is arc length. Isn't that true? Like if a particle is moving, woo, 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 even if it traces over its steps again, you're measuring the arc length of the curve, of the woo, right? That is just, in fact, the arc length formula. So that's kind of an aha moment for us, maybe, that there are these connections. Okay, it's written a little differently. I think we used yesterday. We used dy dt, dx dt and dy dt in these spots, right? Same thing though, right? It's the same notation, different notation. All right, and then the position of a particle is. Well, let's say what this is here. Is this clear? Maybe it's clear right off the bat to you, or maybe not. By the way, lots of fundamental theorem of calculus here. I'm assuming everyone's like okay with why these things are true, but we can step back and be like, oh yeah, by the fundamental theorem of calculus, this is all true. So, what is this piece down here? That is the displacement, isn't it? Displacement from time A to time t, right? Is that clear? And notice because I have t up in the upper limit of integration, that I'm using some other dummy variable instead of t just for fun right there, right? Like we've done with fundamental theorem of calculus lots of times. Okay? Everyone okay with that? All right, and then why am I adding this? Well, because your current position, I want to make sure you're clear in your mind. There are these three questions that people can ask you, all of which can be very confusing in your mind. So I want to make sure you're clear. If someone asks you, hey, we traveled from time 3 to time 4, and what's our displacement? That's this question. What's the total distance traveled? That's a different question. And what's the position? That's a different question, right? We actually care about where we were at the beginning as well, right? Is that clear? Yeah. It's time also, right? But it's like we think of inside these integrals as being like t as being a local variable. So this down here, this whole thing down here is a function of t, isn't it? Like you can plug t values in. But is this a function up here, what I wrote here? It isn't, but we can write it that way. Would you like to? The displacement function, let's call it d. And it's going to be a vector quantity. Displacement of t is equal to the same thing, except, how would you adjust it to like this? Well, it'll just be these things, right? From A to T, right? If you want to start at time A, and you want to know what your displacement is to any time t, not just to time b, then it would be, but of course we can't use t inside the integral too, right? We have to use some other, so what's your favorite letter? Let's use R for Emma Rogers, okay? I don't like using E as a variable, sorry. Because it's already reserved in math for a lot of other things, right? But it doesn't matter. That dummy variable is I know it's like mean to call it a dummy variable, but it is. It's like serving a purpose only here. But once for a given value of t, we're done with. It's like a local variable, right? Say it again. Yeah, this is the, right, exactly. This is, but it's instead of t, we're putting in some other variable, right? And I hope that's okay. Is that all right when we write s down here? Yeah. You probably had the same kind of like unsettling moment when we like did the fundamental theorem of calculus then, right? We're like, why do we have like a t up in there, an s, or like what, right? We had the same kind of questions right back then. Okay, so here's the same curve again. At time equals 0, the particle is at 0, 1. Find the position of the particle at t equals 4. And the total distance traveled. All right, so let's see if we can do both of those things. So the position at t equals 4. Well, that's not very interesting because we have the position vector, don't we? That's what r of t is here. So we can just plug in 4, right? And the position vector that we're going to get is some two-dimensional thing, right? So plug in 4 and tell me what you get. We'll get sine 12, comma, cosine 20, right? And you can approximate those. 12 radians, 20 radians. Make sure your calculator is in radian mode. Okay. Particle from t equals 0 to t equals 4. Okay, that's a little bit of a different question. How do we answer that? So this is position. All right, so one way you could do it is by integrating, finding the velocity function and integrating it from 0 to 4. That's what I know. That's what we just said, Mr. Chase. That's what we should do. But if I give you a position function, is there an easier way to do this? Where were we at 0? I mean, it tells you, actually. I guess I shouldn't have told you, right? But you could plug this in and find out, too, right? Right? If that's true, 0, 1, you can use curly brackets or parentheses, whatever you like. Then once you figure these out, then what is our displacement? This all kind of harkens back to the first semester, doesn't it? This idea. You can compute it 2 different ways. So our displacement vector is this minus this, right? Sine 12, comma, cosine 20 minus 1, right? I didn't actually compute these. You could actually get approximate values of these, right? Does that make sense? How these are different? Could you also find, is this the same answer you'll get if you find the velocity function and integrate it from 0 to 4? Yeah, it should be, right? We'll write that up here too. It's also equal to the integral of the velocity vector, right? On the interval 0 to 4. Okay? Same thing. Yeah. What's that? You'd have to integrate both pieces separately on the calculator, right? Put a comma in between them.
Oh, yeah.
Right? Yeah.
I'm not sure if that's what the question is asking for.
Oh, did I write something wrong? The particle is at t. Find the position of the particle at t4.
So I don't think you unless like it's only one movement, right?
No, I think
It's
you.
asking total distance and what we found is
Oh,
displacement.
you're right. All right. I found it. I did find the displacement though. I just read the question wrong. Yeah. This is the position. This is the displacement. It did ask for the distance though instead. All right. I'm sorry. All right. So how do we find the distance? That we need the velocity for, don't we? So we're going to integrate 0 to 4 arc length, right? It's the arc length formula for this. From 0 to 4 dt. What do we need in here? 3 cosine 3t squared plus negative 5 cosine 5t squared. Sorry, space there. And actually, that's one we can just type into our calculator, right? Yeah. We'll get some positive number that will be the total distance it traveled. Yeah, exactly. Yeah. Displacement is a vector too, right?
The school door will be
Why
closed.
isn't it a number?
Will the following students please come to the main office? Lulu Diawardena and Anthony Fetter.
Right, so if I'm like, it's not telling you where you are, it's telling you where to go, right? So like if I told you, displace yourself by 3 meters northwest, right? No, this is 2 meters, right? I just gave you a magnitude and a direction. I could have instead said, I convert to.
Oh, but that also gives you the back at you. If you squared it.
That would be how far you are away from. That's another. Right. Well, that's displacement is, I don't know, because it gives you information on how to get there. But you're right, that's another meaningful thing when you talk about how far away are you from where you started.
So I'd like to go over here. I just want to know if we're not writing the problems of the worm out. I just want to know, because if I don't get it perfect, that's fine.
Oh, do you have like an 8 or 8.5 or something?
I have an 8.6.
Oh,
Tiger, do you want to catch this?
Like,